Welcome back to Basic Chemical Principles with Richard Blyle. Blah, 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 blah. Okay. Last time we spent a lot of time on chemical reactions, balancing chemical reactions, and chemical reaction types. There's more chemical reaction types. We covered the basics. One of the things I do want to cover, and I think we'll have time, we're not going to do it today, but is redox reactions. Redox reactions are very important. It is redox reactions that keep us alive. Our metabolism is basically a series of redox reactions. But it's not covered in this chapter. So if your book covers it, we're definitely going to talk about it. But I think it's important. This is one of the things where the author and I do not agree on the significance of redox reactions. I want you to understand at least the basics of them, what they mean. But we're going to cover that next week. This week, we're going to go ahead and finish up this chapter. We're going to cover stoichiometry today. When we do chemical reactions, it becomes an academic exercise if we don't do anything with them. There's no point in just showing off around your Christmas meal the fact that you can balance a chemical reaction. Why bother? So today we're going to see why bother. The chemical reactions are around us every day. And we're going to do, we're going to see how chemists use these chemical reactions as we talk today about stoichiometry. Stoichiometry is a big fancy word. Basically, we're talking about chemical calculations. Okay. Let's get into this. For example, let's do one that you know. You've done this reaction before. I know, and if you've ever taken an antacid, you've probably done this reaction. So let's do this one as an example. So here's what stoichiometry means. Suppose we have calcium carbonate. Calcium carbonate is the active ingredient in many brand name antacids. They are used to neutralize stomach acid. Stomach acid. We never talked about nomenclature of acids, but it neutralizes hydrochloric acid, which is the acid in your stomach. There was a biologist many years ago, before they knew what stomach acid was. And the way he discovered what it was, he took a metal test tube, drilled holes in the bottom of it, and put sponges in there and a long string on it. And he literally swallowed the test tube, pulled it back out, and he got the first sample of stomach acid. Well, it turns out it's a very simple acid. It's just hydrochloric acid. So you have calcium carbonate reacting with hydrochloric acid. This reaction will give us calcium chloride. Carbon dioxide, and water. By the way, those additional reaction types, I should mention, they don't belong in that list of 4. they are kind of add-ons. So you might have a single replacement reaction that's also a redox reaction. Or in this case, we have calcium chloride reacting with hydrochloric acid, which is an acid-base reaction. It's also, well, it's kind of a combination of reactions. We're going to see it's kind of a double replacement reaction and a decomposition reaction. So they're kind of additions. We're going to talk about that. So if you want to find out, suppose I have 3 grams of calcium chloride. How many grams of hydrochloric acid can this neutralize? You can ask this a variety of ways. How many grams of hydrochloric acid do we need? Things like that. But if the basic question is this, 3 grams of calcium carbonate, how many grams of hydrochloric acid? Well, first of all, we need to figure out how do you solve something like this? Well, the first step is we have to figure out the compounds. We cannot write a chemical reaction without figuring out what the compounds are. We cannot solve a stoichiometric problem without a balanced chemical reaction. And that's key. In order to solve any of these stoichiometric problems, you must have a balanced chemical reaction. So step 1, let's figure out the compounds. Calcium carbonate. Now, by the way, today you're going to want to have the periodic chart handy. So what is calcium carbonate? Well, we notice that calcium is an alkali earth metal. It is group 2, which means calcium carbonate is a +2 charge. Carbonate, see, now remember, it's not carbide. Anytime you have an IDE ending, it's just an ion right off the periodic chart, a simple ion. If it's not an IDE ending, it is a polyatomic ion. And I believe I asked you to memorize it as a carbonate because you will come across this periodically. But if you have not, carbonate polyatomic ion has the formula CO3 with a -2 charge. So just like before, we do our cross trick. Don't forget, if you put a 2 here without parentheses, it looks like 32 oxygens. So we need parentheses, but the parentheses only go around the polyatomic ion. They only go around the ion to which they apply. But once again, we have a common denominator here. So we can take out the common denominator. And we get CaCO3. Hydrochloric acid, it's just HCl. I'm going to move that. Give yourself a little bit of room in your notes because I'm going to write some things. Actually, I don't have to move it too far because I'm going to work sort of in this space over here underneath the carbonate. We're going to have to do a little quick calculation before we can do anything. But I'm going to give myself a little space under the HCl. Calcium chloride, now that's an IDE ending, which means it's just chlorine in its ionic form. Calcium chloride. Now, chloride is a halogen. It's group 7. So we see the charge of chloride is -1. We do our cross trick. and we get CaCl2. There's no common denominator, and because there are no polyatomic ions, we do not need parentheses. Carbon dioxide is an old nomenclature approach where you actually tell the reader how many of each element you have. Di is Greek for two. So carbon monoxide is carbon mono with one carbon and a single oxygen. Carbon dioxide is carbon with two oxygens. Aluminum trichloride would be aluminum with three chlorines. So this just tells you right out. Carbon is C. Dioxide, oxide means oxygen, but di tells us there are two of them. So we have that. And of course, everybody knows water. We're going to come back to this page, but now that we have all of the ingredients, all of the compounds, let's go ahead and write out our chemical reaction. So we have calcium carbonate, which if you've ever had Tums, you know it's a chalky solid. Reacting with hydrochloric acid to yield, not to equal, but to yield calcium chloride, which will be dissolved at that point. Carbon dioxide. And water. Now, I also want to point out in this particular example, calcium chloride, I said if the polyatomic ions do not change, we can treat them as if it's a single element. In this case, we cannot use that trick because we do not have calcium, we do not have carbonate on the product side. So our carbonate is going to break down into carbon dioxide and probably water. So we have a form of a decomposition reaction here. We also have a double replacement. The chloride from here will replace the carbonate, which means that the calcium is replacing the hydrogen, or in acid speak, it's replacing the hydronium. So now we have all of the players in place. We need to balance this reaction. Is it a balanced reaction? I would ask Kim, but she has stepped away from her computer, or at the very least turned off her video. I do not know why. But that's okay. She's allowed to do that. So we have one calcium on the reactant side, one calcium on the product side. That is balanced. We have one carbon on the reactant side, one carbon on the product side. That is balanced. I'm going to skip oxygen because notice that we have, actually the oxygen is balanced as well, truth be told. But you don't balance, I would not balance oxygen next because we have two oxygens here and one oxygen here. The oxygen shows up in more than one compound. In this particular case, on the product side, it shows up in more than one compound on one side of the reaction. In this case, it's the product side. If this were not balanced, which of those should we balance first, the carbon dioxide or the water? And we really can't tell. So anytime you have an element that shows up in more than one reactant or more than one product, leave it. I don't know if you've noticed this. If you have been practicing balancing chemical reactions, you probably have noticed that there's always one element that just kind of automatically balances itself. So let's leave the oxygen alone. We have one hydrogen on the reactant side. We have two hydrogens on the product side. Do not write this down, but remember, you cannot change the subscript. Because if you change the subscript, you change the compound, and we already figured out what the compound is over here. The compound is HCl. So do not change that subscript. It's really tempting to just sort of real easily and quickly change the subscript and call it balanced, but it's not balanced because you no longer have a valid compound. Or if you do, it's a different compound than what you need. The only thing you can change to balance chemical reactions are the stoichiometric coefficient. So we have 2 hydrogens on the product side and only 1 on the reactant side. So we need to put a 2 in front of the HCl. Now we have 2 hydrogens on the reactant side and 2 hydrogens on the product side. Remember, when you put a stoichiometric coefficient in front of the compound, that applies to every element in the compound. So not only do we have 2 hydrogens now, we also have 2 chlorines on the reactant side, which is good because we notice we have 2 chlorines on the product side. So chlorine is now balanced. And as I pointed out before, 3 oxygens on the reactant side, 2 plus 1 gives us 3 oxygens on the product side. This is now a balanced chemical reaction. To solve a stoichiometric calculation, personally, I like to put what we know underneath each reactant and product from the problem. So we know we have 3 grams of calcium carbonate. So I will put 3 grams here. Okay. And we know we are looking for the hydrochloric acid. So I am actually going to put down question mark, and I always put the units that I'm looking for as well. We are looking for the grams of hydrochloric acid. In the laboratory, excuse me, in the laboratory, we can measure out 3 grams of calcium carbonate. It is literally chalk. If you've grown up in a school that still used chalkboards, and by the way, I far prefer chalkboards to whiteboards. Truthfully, I actually prefer chalkboards to even this tablet. Chalkboards are just very cool. It's just so easy to put problems down and solve them and erase them and yada, yada, yada. But that chalk, if you use white chalk, that's just calcium carbonate. That's all it is. It's the same thing as the active ingredient in your antacid. The only thing different in your antacid is your antacid does have inert ingredients, usually starch, to actually press the pill together and hold it in pill shape. But the active ingredient is just calcium carbonate. So we work in terms of grams. We have scales, we have balances, we can measure out 3 grams if we want to. What we cannot do is, well, I mean, we can, it's just very complicated. We don't think in terms of grams. We don't think. This chemical balanced equation, this doesn't tell us 1 gram of calcium carbonate and 2 grams of HCl. It tells us 1 mole of calcium carbonate and 2 moles of hydrochloric acid. And a mole, remember, is just a number. It's a convenient number, and this is why it's convenient, because 1 mole, we can measure out grams to a convenient mass to give us some number of moles. A mole doesn't have to be a whole number. It can be a fraction of a mole. So here's how you solve any stoichiometric problem. Now, sometimes you can get a little bit weird and complicated and fancy. You can put in solution units, percent, for example, percent iodine, something like that. Sometimes you can put in heat, plus so many calories of heat. And you can do those. Those are all stoichiometric problems, but they all have the same basic approach. Whatever unit you are given, and given does not have to be a reactant. You can say, look, I need 14 grams of calcium chloride, and all of a sudden your starting point is the product, not the reactant. So that starting point can be anywhere along that balanced chemical reaction. And notice we are not doing anything with calcium chloride, carbon dioxide, or water. Our problem doesn't ask about those, so we don't need them. So whatever units you're given, whatever those units are, convert those units to moles. The first step, and by the way, each one of these steps can have multiple steps within them. So if I gave you percent calcium carbonate, you would have to convert from percent calcium carbonate to grams of calcium carbonate. You're still not at moles, so you'd have to take grams of calcium carbonate and convert it to moles of calcium carbonate. But the first overarching step, whatever you're given, convert it to moles. That's the first step. If you're given moles in the first place, if you say, look, I have 3 moles of calcium carbonate, you're done. You're at moles. But whatever it is, get to the moles of what you were given. The reason we balance chemical reaction is so that we can relate two components in that reaction. It can be 2 reactants, as it is in this case. It can be a reactant and a product. It can be 2 products. But what this reaction tells us is that for every 1 mole of calcium carbonate, we have 2 moles of hydrochloric acid. All right? So the next step, take the moles given and convert it to the moles desired. We don't really care how many moles of calcium carbonate we have, because we don't care about calcium carbonate. We're asking about hydrochloric acid. But once we have moles of calcium carbonate, we can convert to moles of hydrochloric acid. So you convert from the moles of what you're given to the moles of what you want. This uses what I call the mole-to-mole ratio. The mole-to-mole ratio, and that's what is most important about these chemical reactions. 1 mole of calcium carbonate to 2 moles of HCl. If I wanted to know calcium chloride, we'd have 2 moles of calcium chloride to 1 mole, 2 moles of hydrochloric acid to 1 mole of calcium chloride. See? All I'm doing is reading off those stoichiometric coefficients. And remember, if there's no stoichiometric coefficient, 1 is assumed. Once you get the moles of whatever it is you're asking about, your moles of desired, this is why I put down question mark grams, because the final step, take moles of what you want, convert it to the final units of what you want. There's a certain symmetry. There's a certain symmetry in these stoichiometric calculations. You go from the units that you're given to the moles of what you're given, convert that to the moles of what you want, then you take the moles of what you want and convert it to the units of what you want. This is stoichiometry right here. Except I just crossed out ratio. Don't cross out ratio. That ratio is important. So the first thing we need to do is convert from grams of calcium carbonate to moles of calcium carbonate. How do you do that? Well, keep in mind, and I think I mentioned this to you briefly, on the periodic chart. Can I pull up my periodic chart, do you suppose? Are you still on? I'm still on. Let me see if I can pull up my periodic chart real quick. Sorry about this. I should have had this open already. I didn't think about it, but it would be a good thing to open up. So let's open this up real quick. And you know why it's not showing up is because it's not a Word document. It's a PDF. So let me open it up as a PDF. There it is. File not found. That is not a good sign. It must be, don't you think? Well, shoot, I'm not finding it. Okay. You know why I'm not finding it? Because it's in my remarkable. I am so sorry for this. I'm giving you time. You see, I'm doing it on purpose. I'm giving you time to look up your periodic chart. That's a lie. I'm being an idiot. I just forgot that I already moved it onto my remarkable. So I can just open it up in my remarkable right there. Look how easy that was. So here's your periodic chart. And last time we talked about how much it gives us in information on electronic configuration. If we zoom in, let's find calcium down here. Calcium, it tells us, first of all, it's group 2, which you can't see right now because of the way I'm zoomed in. So it's group 2, which means it's a +2 charge. That's one thing the periodic chart tells us. It tells us that it's atomic number 20, which means it has 20 protons. Remember, the atomic number does not really tell us the number of electrons. For example, calcium +2. It's +2. Electrons, remember, are a negative charge. So if it's +2, that means it lost 2 electrons. As in its elemental form, calcium has 20 electrons because the number of electrons for an element does equal the number of protons. But to be an ion means it's lost its electrons because it's +2. It lost 2 electrons. It started with 20 electrons. 20 minus 2 gives us 18 electrons. So that's why the atomic number is the number of protons, not the number of electrons. So we can figure out how many electrons based on the atomic number and the charge, but usually we don't really need to know that. We can figure it out. It's easy. The third thing that it gives us that we have not spoken about is this number right down here. What is that? 40.08. And I mentioned to you this before, so this is where we're going to play along. If you have your periodic chart, you're going to want that. I've mentioned it briefly to you before, but I never really told you what it means. Anytime you have an atomic number, so calcium, I'm going to do it down here. I don't need it down here, but this is where I'm going to write it. Anytime you see that atomic mass, always add the units grams per mole. This is the gateway. This is the door between what we can do in the lab, measuring mass, and what we do in our conscience, how we think about it, working with moles. This is how you convert from grams to moles and moles to grams. It's a difference between the practicality of lab functions and the theoretical mole. So to figure out the formula mass, we're going to talk about here, there are three terms that you're going to hear frequently: atomic mass, formula mass, or compound mass. And the only thing, they're all the same thing. The only thing that differs is if you're talking about an element, a compound, a covalent compound, or an ionic compound. So atomic mass would be the atomic mass. This would be the mass of an element. 40 grams per mole is the atomic mass of carbon. If we get the formula mass, let's see, formula mass applies to an ionic compound. We need the formula mass of calcium carbonate. If we're talking molecular mass, that's for a covalent compound. So ionic, formula mass. A single element, atomic mass. Or for a covalent compound, we get molecular mass. Three different terms, but they all kind of really mean the same thing. My students frequently would interchange these and not quite use the correct one, but every time they would say, what's the atomic mass of calcium carbonate? Well, no, that should be the formula mass, but I knew what they were talking about. So don't worry too much about these distinctions. Just know that if you're talking about molecular mass or formula mass or atomic mass, it's all basically grams per mole. It's all the same thing. So how would we get the formula mass? Now, we don't need the formula mass of calcium chloride, but how do you get the formula mass? Well, the formula mass is nothing more than the sum of the atomic masses of every element in the formula or the compound. So calcium carbonate would be the mass of 1 mole of calcium, because the subscript here is 1, and the mass of 2 moles of chlorine. Notice that I am not worrying about the stoichiometric coefficient. Whatever is here in front, we don't need it yet. We're just going to get the formula mass of 1 mole, and we need calcium carbonate, and we're going to get the formula mass of 1 mole of hydrochloric acid. So calcium is 40.008. Yeah. Carbon, I remember because I use it so frequently. It is 12.01. And oxygen, 1 oxygen is 16.00. These are all on your periodic chart. Do you have to memorize these? No. Will you memorize them? Depends on how much you work with them. If we do stoichiometry and organic chemistry, believe me, you are going to remember that calcium is 12.01. I'm sorry, carbon is 12.01. Oxygen is 16. So to get the formula mass, we have 1 calcium plus 1 carbon and 3 oxygens. Whip out your handy dandy calculator if you want to play along. And you see the calcium carbonate has a formula mass of 100.09. Always, always, always include the units grams per mole. We need that. So I'm going to put that right down there, right underneath calcium carbonate. Hydrochloric acid, hydrogen is 1.008 or 1. Yeah, let's go ahead and use it. It's too many sig figs. Actually, I put it above last time. Let's be a little consistent. Chlorine is 35.45. Get the feeling I've done this a couple of times. So we have one hydrogen with a mass of 1.008 and one chlorine with a mass of 35.45. If you round it to the appropriate number of sig figs, you would end up with 36.46 grams per mole. Did I do that right? Boy, it's a simple addition, and I just felt like I had to. Yeah, 36.46. Notice that I'm tired. It's 36.46, not 36.44. Add the units, grams per mole. Just make that your mantra, grams per mole. Notice I ignored the stoichiometric coefficient 2 at this step. Okay, I ignored the stoichiometric coefficient 2 at this step. So let's do our calculation before we take our break. So we have, remember, the difference between a starting point and a conversion factor. Gram per mole has 2 units. That's a conversion factor, 2 units. Grams, we have 3 grams. That's your starting point. Kim likes it when I set up my problems like this. So let's go ahead and do it using our, this is a very clean look, so I don't blame her. This is good. So we start off in the numerator with 3 grams of calcium carbonate. If you want, you can put a 1 down here in the denominator. It's unitless, so it doesn't really matter. Notice that for this problem, I'm including what the compound is, because in stoichiometry, we're always going to change from one thing, from one compound to something else, from one compound to a different compound, one compound to an element, one compound to heat, one element to another element, one element to a compound, one element to heat, heat to one compound, or heat to one element. There's always a change. So we may as well put that here so we don't forget. Now, we need to convert from the units given to moles. Is there anything here that converts specifically calcium carbonate to moles? Oh, look, here's our formula mass. Grams on top, moles on the bottom. Remember, in stoichiometry, we're always looking to cancel a unit. So we have grams on top, we need grams on the bottom. And this refers to calcium carbonate. Because gram is on top, remember, it's always grams on one side, moles on the other. So this will give us moles of calcium carbonate on top. How many? Remember, the number stays with the units. It's 100.09 grams per, if there's no number, one is implied, 1 mole. So it is 100.09 grams. So the gram stays with the number. What's up here? What's this number? If there's no number, 1 is assumed. So I'm just going to leave this blank because 1 is assumed. Now we're at moles of what we're given. So we're at this step. The next step is to figure out moles of what we want. We don't want moles of calcium carbonate. We want moles of HCl. Once again, still using factor label, but this time we're going to use the stoichiometric coefficients. What goes on top, what goes on bottom? We want to cancel the calcium carbonate. So it goes on the bottom. And we want the moles of HCl. It will go on top. By the way, grams of calcium carbonate cancel. I forgot to do that. Now we're looking to cancel moles of calcium carbonate. Usually, there's nothing wrong with your notes. Usually, just to make sure we don't confuse, I like to cross in different directions. Okay, the question now is, what numbers do we need here? Well, these numbers come right out of the stoichiometric coefficient. So how many moles of hydrochloric acid? 2. Comes from that stoichiometric coefficient. This time, I'm going to go ahead and write down, because specifically we have 1 mole of calcium carbonate, so we know that we did that correctly. Again, 1 is assumed, so you don't need it. Now we have used our mole-to-mole ratio to get to moles of what we want, but we don't want moles of HCl. We want grams of HCl. So how do we do that? Well, again, here's a unit, here's a conversion factor that has both moles and grams. So once again, we have 36.46. Oh, shoot. Okay, that's fine. What has to go on the bottom? We want to cancel the units moles. So we have moles of HCl on the bottom. We want grams of HCl on top. How many grams? 36.46. Last time I canceled this direction, so let's cancel this direction this time. And notice that we are now at the units that we want, grams of HCl. This is the beauty of the factor label method. If you do it correctly, you should get the units of what you are seeking, and we do. We have grams of HCl. Now we just punch it up. So anything on top we multiply, anything on the bottom we divide. So we have 3 grams of calcium carbonate divided by 100.09 grams. My calculator, I can just do this straight out. Your calculator, you may not be able to. If you put divided by there, it may assume that everything after that is going to be divided by. So you have to practice with your calculator. We're going to multiply now by 2 moles. And 36.46 grams, so times 36.46 grams. This is a good chance to make sure you are using your calculator correctly. So when you do this calculation, you should get 2.2, should be 2 significant figures, because we have 2 sig figs here. We have 2.2 grams of hydrochloric acid. That is our first stoichiometric calculation, and it's a good example because it shows how you skip the stoichiometric coefficients when calculating molecular mass. Molecular mass is always per 1 mole. always. It doesn't matter what this number is. It's always per 1 mole. It also shows us how to use the stoichiometric coefficient with something other than 1-to-1. A lot of times these chemical reactions just come up 1-to-1. Not terribly instructive. So we got that. Yeah, this was a good example. It's 10:45. I'm going to take a break. I'm the only one here because my excellent student has stepped away, at least momentarily. So I'm going to take a 5-minute break for me. Oh. All right, welcome back. Last time we did an example, and it turned out to be just a beautiful example for a first time. As a professor, you pull these reactions out of the air because I've done it often enough. I can do that. And sometimes they turn out to be beautiful examples, and sometimes they're just train wrecks. This one turned out to be quite a beautiful reaction. Let's do another reaction. Let's do another stoichiometric calculation, another example for you. Single replacement this time. I'm going to do a calculation where you will understand how industrially there's something that this might be useful for. Usually, industrially, they don't really care. Well, I mean, they can. If they have a vat of hydrochloric acid and they're adding calcium carbonate to neutralize it, they might need to know how many grams of calcium carbonate they need. But here's one of my favorite demonstrations. I talked about this last time, the Christmas tree demonstration. You take copper to nitrate. I'm going to do this. Nope, you take copper. I apologize. So you take copper and you want to react it with silver nitrate. I always like nitrates because they're cheaper than day rates. You end up with, as a product, copper 2 nitrate. This is a single replacement reaction. And elemental silver. The demonstration is sometimes called the silver Christmas tree demonstration, because you take your copper, and it has to be really clean copper. Clean it with hydrochloric acid before you begin. You make a nice little coil out of it, so it's kind of in the shape of a Christmas tree. You dip it in the silver nitrate, and the silver crystals grow on the copper, and it's really a beautiful demonstration. Anyway, suppose I want 100 grams of silver in the end. How many grams of copper, how many grams of copper would that require? You know what? No. How many grams of silver nitrate do I need? Let's do silver nitrate instead of copper. How many grams of silver nitrate? So in this case, we're actually taking silver and converting it to another form of silver. We're taking silver compound, converting it into silver metal. When you buy silver nitrate, the price that the chemical companies charge you is very much based on market price of silver at the time. But if you took silver nitrate, it's just a white powder. Actually, I'm sorry, it depends. If it's been exposed to the light, it quickly changes. Silver nitrate was the compound that they used in early black and white photography. Because when it's exposed to sunlight, it becomes silver oxide, which is a dark element, a dark compound. So silver nitrate is white. You put a very thin film, basically in a cellulite base that holds it in place. They expose it for a moment to sunlight, although back then they had to open up the lens for quite a long time to get enough light to actually do the reaction. And all of a sudden you have white silver where there was no light, and you have dark silver where there is where it was exposed to sunlight, and that was the photographic negative. So this has actually some interesting historical concepts there. Anyway, before we do anything, let's go ahead and figure out our atomic and formula masses. Oh, well, no, we also have to figure out our compounds. So copper, of course, is just copper. Silver nitrate. You should remember that nitrate is NO3 with a -1 charge. Now, something that you would not know off the periodic chart unless you've been told, silver is always +1. Is there a reason for that? Not really. What's really happening is silver is trying to get rid of the s orbital electron and using the remaining s orbital electron to fill the d orbitals. So it does weird things. Like I say, those transition metals do weird things. Silver is always +1 in a compound. Copper 2 nitrate. Remember that 2 does not tell us how many coppers. This 2 tells us the charge or the oxidation state. By the way, that's something that you're going to learn. When you hear the term oxidation state, think charge. Okay, so you'll hear me sometimes say oxidation state, think charge. Okay, so that 2 tells us the oxidation state of copper. So copper has a +2 charge. Nitrate, we've said this before, polyatomic ion has a charge of -1. So you do your cross trick. You have 1 copper for every 2 nitrates. And again, looks weird, looks like 32 oxygens. We have 32 nitrates, 32 of those polyatomic ions. So we need to use parentheses to say, no, we have 2 nitrates, not 32 oxygens. And let's see, we do that. And of course, we have just plain silver. We really only need the masses, the formula masses for the 2 things we're looking for, silver nitrate and silver. We do not need the formula masses for copper or copper 2 nitrate because they're not going to show up in our calculations. Silver, if you look at your periodic chart, is 107.9 grams per mole. Remember, always, always, always add grams per mole. Usually you use a sideways slash like this. This is the same as 107.9 grams per mole. So don't try and use this sideways slash in the factor label method. That sideways slash will mess you up. Use the horizontal slash. Silver nitrate. You have 1 silver. And down here, we already see, we looked it up, 107.9 grams per mole. When I'm calculating formula masses, I usually don't put the units in yet. We have 1 nitrogen, which if I'm remembering correctly is 14.01. I was not remembering correctly. And we have 3 oxygens at 16.00. So for silver nitrate, This is a scientific calculator. It may look funny to you. This calculator has been with me since the 80s when I was an undergraduate in chemistry. And you'll find that it's not fancy. You can't do graphs or anything fancy with it, but I'm so used to it. It's like an old friend. So I know how it works, and I know that I can do calculations and how to, it uses scientific, it's a scientific calculator. So the formula mass is 169.91 grams per mole. A scientific calculator simply knows order of operations. It's not necessarily a calculator with all those fancy trig units like sine and cosine and tangent. It just knows order of operation. Here's a real simple test to see if your calculator is a scientific calculator. Punch in 1 + 2 × 3. In this order, no parentheses, no nothing. 1 + 2 × 3. If you have a scientific calculator, it will give you the correct answer. If you get 7, you have a scientific calculator. A scientific calculator does the order of operations correctly. If it's not a scientific calculator, you will get 9, which is wrong. Because it will just do the operations in the order entered. There's so many on Facebook. There's so many of these stupid little quizzes. Hey, figure out this. If you can figure this out, you're a genius. And usually it's just, if you know the order of operations, you can get it. But that's all a scientific calculator is. So we have our formulas. We have stepped ahead a little bit and gone ahead and calculated the formula masses for what we know we're going to need. Now, let's balance our chemical reaction and do the calculation. So we have copper, which is a solid, reacting with silver nitrate, which is a clear, colorless. Oh, give yourself a little room in case you need to put in a stoichiometric coefficient there. Clear, colorless liquid solution. It's a solution. So it looks like water. We're going to end up with copper 2 nitrate, which is a beautiful blue liquid solution, and silver solid. We want 100 grams of silver. We need to know how many grams of silver nitrate we need. But before we can do the calculation, the stoichiometric, the reaction must be balanced. It must. We might not, I'm not going to do that. Anyway. So, again, if you want, you can put that little table down here of elements. I just don't work that way. I just notice we have 1 copper on the reactant side, 1 copper on the product side. It is balanced. In this case, the nitrate never breaks down. Nitrate is nitrate. So I can actually think to myself, okay, well, first of all, let's do silver. 1 silver on the reactant side, 1 silver on the product side. But I can think to myself, look, I have 1 nitrate, not 1 nitrogen, not 3 oxygens. I have 1 nitrate on the reactant side, 2 nitrates on the product side. That means our nitrates are not balanced. Because we have two nitrates on the product side, I need a stoichiometric coefficient here. This gives me two nitrates on the reactant side. And here we have two nitrates on the product side. But doing that, now the silver is no longer balanced because now we have two silvers on the reactant side, only one on the product side. So we needed two in front of the silver. Okay? What we're given in this problem is not what we're given in the lab. In the lab, we're given silver nitrate, but for the problem, we're given the product, silver. So, oh, by the way, since we've calculated them, let's go ahead and put down our formula masses, 169.91. And silver was, what was it? 107.9. So what do we start with? Well, do not start with a question mark. That's what we're trying to end with. We end with a question mark. What we're given is 100 grams of silver. And we have begun our calculation. First step in stoichiometry, convert from whatever unit you're given to moles. We need moles of silver. And fortunately, we have a conversion factor here. It converts from grams to moles. Is this right? Well, Kim has again stepped away from her computer. And my computer just woke up. Amazon is wondering what I want from it. Anyway, this is what, thank you. This is where I said, if you are, please stop interrupting me, Amazon. If you are doing your factor label method correctly, it will tell you when you make a mistake. Grams cannot cancel here because I put it on the wrong side. If I did this correctly, the unit that I would be at right now would be grams squared per mole. That doesn't help me. We need moles on grams on the bottom. Here's another mistake that a lot of students will make. Come on. They will simply change the units. You cannot do that. The 107.9 stays with the unit. Come on. Boy, this thing is getting worse. So we actually need grams on the bottom. And it is 107.9 grams of silver. Well, I usually don't put 1, but this time I did. I'm going to leave it. Why not? Doesn't hurt anything. 107.9 grams. We need the grams to cancel. Grams in the numerator, cancel grams in the denominator. Now we are at moles of silver. Once we're at moles of what we want, now we use the mole to mole ratio. And you have to be a little bit careful here. We have 2 moles of silver, and notice we need moles of silver on the bottom. And you just read these right off of that balanced chemical reaction. We have 2 moles of silver nitrate on the top. Now you'll notice that the 2's actually cancel. I have written it down as a 2-to-2 mole-to-mole ratio. I could have gone ahead and just reduced it in my head and just put it down as a 1-to-1 molar ratio. The problem is when I do that in my head, sometimes I put the wrong thing. I'll reduce one side but not the other. And in the calculation, I might set it up to 1 moles of silver nitrate to 2 moles of silver. That would put me off. I'd be 50% off. So I go ahead and I keep the stoichiometric coefficient exactly as they are in the balanced chemical equation. The weird thing is when I'm doing the calculation, I'm not going to put in ×2 divided by 2 because I know those will cancel. So when I'm actually putting in my calculator, I go ahead and reduce it. But at this step, personally, I leave it according to the stoichiometric coefficients, even if they do cancel. Now we're at moles of silver nitrate, but we don't want moles. We want grams of silver nitrate. Well, here we have grams per mole again. The moles of silver nitrate cancel, and we are left at grams of silver nitrate, which is what we want. So let's do this calculation real quick, and it'll give us enough time to cover one more topic, which I kind of was hoping I would get to today. So 100 grams of silver divided by 107.9 gives us actually 0.93 moles. 2-to-2 ratio, which I'm not going to worry about, 69.91. Did I get 69.91? Apparently I did. Gives us a total. We're going to need 157.5. We're going to need 157.5 grams of silver nitrate. The book talks about theoretical yield and percent yield and all that fun stuff. We're not going to go through these calculations. It just kind of complicates things a little bit, especially when you talk about limiting reagents and yada, yada, yada. But I want you to understand the concepts. So let's talk about the concepts. First of all, let's talk about limiting reagent. These are things you'll do in the lab. But since we're not doing a lab, you don't need to know them for this course. But I want you to understand the concepts because your children may need to know these. The limiting reagent is what runs out first. Once one of the reactants runs out, once one of the reagent is just one of the chemicals you use in the chemical reaction. So here our reagents are copper and silver nitrate. Once one of those runs out, game over. The reaction stops. There's no more reactant. Doesn't matter. And there's always going to be one reactant or another excess. There's always going to be one left over. So if I said that I started off with 25 grams of silver nitrate and 10 grams of copper, I would need to figure out the limiting reagent because the rest of the calculations will be based on the limiting reagent. And what you do is you figure out how many moles of each reactant. The one that has the fewer moles, well, and then you have to figure out based on the mole-to-mole ratio, which one runs out first. There's a series of steps to this, and like I said, we're not going to get into it. But just know the limiting reagent is what runs out first. In this reaction, we are assuming that the silver nitrate is the limiting reagent. We have a wire of copper. That's going to be a lot of copper. So we're assuming we have more than enough copper. It's in excess. What's going to run out? Well, our 157.5 grams of silver nitrate will run out first. It is the limiting reagent. What I have calculated here is theoretical yield. Theoretical yield is what you should get in theory. In theory, we should get 157.5 grams if we are perfect. That's why it's called theoretical yield. According to these calculations, theoretically, if we measure out 157.5 grams of silver nitrate, we should get 100 grams. Actually, our theoretical yield here is how much of the product. So theoretically, we should get 100 grams of silver. We should. In practice, though, we are not perfect. The reaction may not run to completion. We may not give it enough time to run to completion. We may measure out the wrong, we may not quite have 157.5 grams of silver nitrate. So maybe we don't have enough silver nitrate, or maybe we have too much. Maybe when we filter out the silver, we're going to lose some of it. Just mechanical error. So there's always going to be some kind of an error. So our theoretical yield is what we should get. Our actual yield is what we do get. With all of our imperfections, what do we actually get? That is our actual yield. So in order to do actual yield, you can't do a calculation to figure out, well, I mean, I suppose you could. But basically, it's your human flaws. You know, we're expecting 100 grams of silver. That's our theoretical yield. Maybe we get 93 grams of silver. That's our actual yield. That's what we actually end up with in the end. Percent yield is how close are we to our theoretical yield. So there's a little formula. Take your actual yield, which is what you just got running the experiment, divided by your theoretical yield, which is what you should get if you were perfect. Now it's a percent. Cent means 100. Percent means per 100, which is why we multiply by 100 to get the percent yield. How close are we in percentage? Percent, cent means 100. A century is 100. There are 100 cents in $1. So just remember, percent literally means per 100. Is it possible to get a percent yield over 100? Yes, it is. It happens frequently in the lab. Does that mean you're better than perfect? No. You did something. Most of the time, the reason students will get greater than 100% is the product is not completely dry. If they do not dry completely, you have a little extra mass there with the solvent, and you're going to get greater than 100%. But that I'm glad we covered that. We're not going to do a percent yield calculation, but you know how to, and now you understand what they all mean, which for our purposes in this course is sufficient. So what we've covered today was stoichiometric calculations, and now you see the power of a balanced chemical reaction. Industrially, they're always trying to figure out percent yield. They want the best possible procedures. They're always trying to figure out how much reactants they need in order to get the product, or how much product to expect, which will factor into price. That's it for me. I hope that you learned a little something, and please don't be late for your next class. Oh, wait a minute. And the record.